Abstract. Federated learning has recently received a lot of attention for large-scale privacy-preserving machine learning. However, high communication overheads due to frequent gradient transmissions decelerate federated learning. To mitigate the communication overheads, two main techniques have been studied. First, local update of weights characterizing the trade-off between communication and computation, and, second, gradient compression characterizing the trade-off between communication and precision. To the best of our knowledge, studying and balancing those two trade-offs jointly and dynamically while considering their impacts on convergence has remained unresolved, even though it promises significantly faster federated learning. In this paper, we first formulate our problem to minimize learning error with respect to two variables: local update coefficients and sparsity budgets of gradient compression, who characterize trade-offs between communication and computation, precision, respectively. We then derive an upper bound of the learning error in a given wall clock time considering the interdependency between the two variables. Based on this theoretical analysis, we propose an enhanced federated learning scheme, namely fast federated learning, FFL, that jointly and dynamically adjusts the two variables to minimize the learning error. We demonstrate that FFL consistently achieves higher accuracies faster than similar schemes existing in the literature. Introduction. Federated learning is a training paradigm where a large number of workers collectively train a model using stochastic gradient descent, SGD. Each worker holds a local, often private, training dataset, with which it contributes to training a global model. Specifically, in each federated learning round, each worker computes the error of the global model by forward propagating the samples of its own dataset through the model, followed by comparing the model's outputs with samples labels and applying an appropriate loss function. By backpropagating this error, each worker calculates the gradients. All workers then send their gradients to the server, who updates the global model and sends the updated model back to all the workers. At this point, one federated learning round is completed. After a number of federated learning rounds, the global model converges. Federated learning has recently become popular for the following reasons. First, federated learning enables privacy-preserving training as workers only share their gradients with the server. That is, federated learning makes it possible to train a model from the entire datasets of workers without any individuals having to reveal their local datasets to other workers or the server. This characteristic of federated learning technology renders it apposite to many applications, the most popular of which is Internet of Things, IoT, where the data from organizations, hospitals, homes, smart home, and vehicles, Internet of Vehicles, presumably needs to be collected for processing, inference, and decision-making. Federated learning removes the need to collect the raw data in using machine learning for IoT. Thereby it ameliorates the privacy of IoT. Second, federated learning is an exemplar of edge intelligence, which is the offspring from the union of mobile, edge computing and artificial intelligence, AI. Edge intelligence advocates for pushing the intelligence down from clouds to the proximity of end users by implementation of AI applications on edge devices, thereby promising better privacy and reliability with lower latency and cost. Federated learning, correspondingly, can be used to facilitate training of large-scale models by parallelizing the computation of gradients on edge devices. Moreover, federated learning allows inference to be performed on edge devices, and thus, fulfills the goals of edge intelligence. Third, federated learning addresses the intelligence democratization issue. In the AI market, big companies possessing a large amount of data plus computational and storage facilities can get the monopoly of AI businesses while small firms have no chances in this competition. Federated learning enables small businesses to play a role in the market as they do not require a massive amount of data at a data center, nor computational and storage facilities. Unfortunately, the empirical speedup for training offered by federated learning often fails to meet the optimal scaling, in the number of workers, that is ideally desired. It is now widely acknowledged that this speedup saturation is mainly due to the communication overheads, which are largely attributed to frequent gradient transmissions from workers to the server. As the number of parameters in the state-of-the-art models scales to a huge number, typically hundreds of millions, the size of the gradient scales proportionally. The communication bottleneck becomes even more pronounced, particularly when the workers performing federated learning are wireless devices, for example smartphones and sensors, which communicate through wireless channels and suffer from low bandwidth, intermittent connections, and expensive mobile data plans. To mitigate the communication overhead problem and hence speed up learning, in the literature, two main techniques have been studied. The first is local update, characterizing the trade-off between communication and computation, and the second is gradient compression, characterizing the trade-off between communication and precision. Each of these techniques will be discussed in the following. In the local update technique, within each round many local updates are performed, instead of only one update. Local update presents a communication-computation trade-off as local update coefficient determines the ratio of computation to communication. The authors of previous works showed that local updates can significantly alleviate frequent gradient transmissions. Formulating the error convergence bound in terms of local updates, adaptive communication dynamically optimized the local update coefficients to accelerate convergence while retaining accuracy. Authors of adaptive communication also showed that the communication-computation trade-off introduced by local update coefficients should be dynamically balanced over the course of learning. In a later work, the same issue was addressed, but assuming that the loss function was convex. Performing binary compression and benefiting from local updates, sparse binary compression could significantly decrease communication overheads. Gradient compression presents the communication precision trade-off, i.e., how much compression is productive in different rounds. Gradient compression methods fall into two categories: gradient quantization and sparsification. Gradient quantization approaches the problem of communication overhead by sending a compressed, quantized version of the gradient. Turngrad used 2 bits for each element of the gradient, and authors mathematically proved the convergence of Turngrad under the assumption of a bound on gradients. Quantized SGD, QSGD, investigated the effects of 2 bits, 4 bits, and 8 bits quantizations on different layers of neural networks and showed that the networks converge. Some authors even went further and quantized the gradients to 1 bit. In other works, similar quantization techniques were exploited. Sparsification technique aims to sparsify gradients in order to send only the significant elements of the gradients instead of all. Sparsification techniques fall into 2 categories depending on in what domain the sparsity is sought for. Some researchers assume that gradients are sparse in their original domain, while others find some transformed domains more appropriate. Following the first approach, the scheme proposed in a recent work sparsified gradients by setting insignificant entries to 0, where insignificant entries were those entries whose values were between top 0.05% and bottom 0.05%. The authors then used run-length codes to encode the gradients before sending them to the server. In another work, a similar scheme was studied. The second approach for sparsification aims to find another domain for gradients in which they are more sparse than their original domain. In a seminal work, gradients were transformed to the singular value decomposition (SVD) domain to exploit more sparsity, helping to mitigate the communication overheads. Also, the authors stated that Turngrad and QSGD were special versions of their proposed scheme under certain circumstances. The authors in an interesting paper proved why in general, big matrices are often low rank. In the literature, each of the aforementioned techniques, i.e., local updates and gradient compression, has been individually demonstrated to mitigate the communication overheads in federated learning, leading to considerable speedups. Specifically, dynamically determining local update coefficients to balance the communication-computation trade-off has been studied, but without considering any compression of gradients. Meanwhile, static gradient compression, communication precision trade-off, has been studied, but without dynamically adjusting local update coefficients. Based on these works, it is expected that conjoining the two techniques would be even more effective in reducing the communication overheads, thereby accelerating federated learning. To the best of our knowledge, however, studying and balancing those two trade-offs jointly and dynamically while considering their impacts on convergence, from both theoretical and empirical perspectives, have not been done in the literature. This unexplored, yet important problem motivated our work. In this paper, we propose such jointly adjusted, balanced scheme, namely fast federated learning, FFL, which jointly and dynamically determines the local update coefficients and sparsity budgets of gradient compression. Our main contributions in this paper are as follows. As the first work in the literature, we formulate our federated learning problem to minimize the error of the global model in a given wall clock time with respect to both local update coefficients and sparsity budgets, which are respectively demonstrated to characterize the trade-off between communication and computation and the trade-off between communication and precision. We derive an upper bound of the error of the global model in a given wall clock time considering the interdependency between the two variables, the local update coefficients and sparsity budgets. Using the derived error upper bound, we propose an enhanced federated learning scheme, FFL, which jointly and dynamically determines the two variables to accelerate learning. Our analytical results include almost all of the unbiased compression techniques. This is because our formulation for compression is based on atomic decomposition for sparse representation, which is a popular technique for compression from compressed sensing. We demonstrate that FFL consistently achieves higher accuracies faster than similar schemes existing in the literature. Note number 1. Achieving fast federated learning is the main concern of our proposed scheme. However, achieving fast federated learning and communication-efficient federated learning should not be conflated. Although these two objectives overlap, correlate in practice, they are still different at a conceptual, theoretical level. Achieving fast federated learning requires communication efficiency, but it is not limited to it. For achieving fast federated learning, every time consumer should be taken into account. A. Downlink communication time from the server to the workers. B. Time for local training of neural networks, i.e., computation time, at the workers, and C. Uplink communication time from workers to the server. In a special case, when the communication data rate is low, the communication time becomes the dominant time consumer and the bottleneck. In such a case, achieving fast federated learning reduces to achieving communication-efficient federated learning. Note number 2. The problem of achieving fast federated learning can be framed as to jointly and dynamically find balances considering the two inherent trade-offs. First, communication computation and, second, communication precision. The first trade-off is characterized by the local update coefficient, for which striking a balance matters because one extreme, high communication and low computation, slows the convergence whereas the other extreme compromises the accuracy. Either way, the learning is decelerated. The second trade-off is characterized by the sparsity budget of gradient compression where seeking a balance is imperative since high compression, imprecision, one extreme, stalls the learning process while no compression incurs heavy, unnecessary communication overheads. Having that framing of the problem in mind, we will mathematically formulate our problem to minimize the learning error in a given wall clock time with respect to local update coefficient and sparsity budget of gradient compression. To read our paper, please refer to the links given below.